This is the min cost climbing stairs problem, which we want to try and solve with minimum complexities of on time and on space. We're given an integer array cost, where cost I represents the cost of the ith step on a staircase. Once you pay the cost, you can either climb 1 or 2 steps. You can start from either step 0 or step 1, but the goal is to find the minimum cost to reach the top of the staircase. So you're paying a toll for every step you take. In the examples, we can see that we've got the first array of 10, 15, and 20, and we can reach the top of the staircase by jumping to step 1 and then getting to the top. That will cost us $15, so a very expensive staircase. In example 2, we can maneuver in such a way that we're paying 1 for each step that we actually touch. However, it might be quite difficult to work this out. In any case, it will pay off because you'll be paying $6 rather than touching any of those steps that have 100 on them. In any case, let's look at the 4 methods we can use to solve this most optimally. You have a choice between A, greedy, B, binary search, C, DP with memoization, or D, bubble sort. I'm going to pause for a couple of seconds while you make your choice. So, for those of you who were able to get this, congratulations. And for those of you who just want to see the code, the answer here is of course C, DP with memoization. We won't approach the brute force approach at all. We'll just talk about our optimized approach. In this, we're using DP with memoization, and you can see we're making use of this member function climb, which calculates the minimum cost of climbing the stairs. This uses memoization to store previously calculated results, as well as recursion to compute the minimum cost based on the different choices we have at each step. It checks if the result for the current index is already calculated and stored in the memory array like so. If so, it returns that pre-calculated result. Otherwise, we're going to calculate the cost for the next step and the step after that using recursion, and store the minimum cost in this variable ret. The entry point for the solution is this min cost climbing stairs function. All it's doing is initializing the memory array with -1, and that will indicate that no results have been calculated yet. We also set the cost vector up, enabling it to be called by the climb function. And we call the climb function itself with indices 0 and 1, which represent our possible starting points for ascending the staircase. Whatever happens, we'll be returning the minimum cost between these two starting points. So, let's go through this line by line. I think it's quite a short and simple piece of code. The first thing we're doing is setting up this constant max, which is the length, the maximum possible length of our number of steps. After that, we're setting up our memory array, which will store our calculations for each step, hopefully storing the minimum cost each time, and this vector cost, which we'll be using to access the cost at each step in our climb function. As mentioned, the min cost climbing stairs function is the entry point to our solution, and in it we're doing 3 things. We're assigning the cost vector to the global cost vector here, and then initializing the memory array with -1, which will be used to indicate that no results have been calculated for a specific index yet. Finally, we're going to return the minimum cost between starting from the starting index 0 and climbing from the starting index 1. So hopefully we will get the minimum cost using that. But let's look at the climb function and see how it works precisely. The first thing we're checking is whether the current index is beyond the last step, i.e. greater than or equal to the size of the cost vector. If that's the case, it means we've reached or surpassed the top of the stairs, in which case we return 0 as our cost. After that, in these lines, which look complicated but are not, we're checking if the result for the current index has already been calculated and stored in our memory array. So this is a reference variable ret, which looks at the memory index. And if ret does not equal -1, it means we've already calculated a result for this index. In that case, we return the pre-calculated result rather than recomputing it down here. By the way, we're always storing the reference to the result in this ret variable, which is why it's set up by reference. After that, and assuming we've got through without returning ret, we're going to look at these variables. So we calculate the cost for the next step by adding the current step's cost, which is cost index, to the minimum cost of climbing from the next step, which is climb index plus 1. We can calculate the cost for skipping the next step and directly climbing from the current step to the one after the next step, going up 2 steps, by adding the current step's cost index, to the minimum cost of climbing from the step after the next, which is given by climb index plus 2. Finally, for this function, we've got a very easy return. We're returning the minimum cost between our 2 choices, next and skip, as the result for the current index. And that's everything. We should have been returning the minimum cost between climbing from index 0 and climbing from the starting index 1. So that's another problem solving session completed. I appreciate it's not the most visual solution. To check out a good visual solution taught by someone who really knows what they're doing, I recommend checking out the link which is in the description to this video. Dr. Ibrahim does a really comprehensive job with numerous dynamic programming problems here. As for our application, we'll look at the problem statement and possible solutions one more time, and you should remember that to solve min-cost climbing stairs, we can use dynamic programming plus memoization. This is a brief explanation as to why, and if you need the code, you can check it out in C++, Python, and Java as well. I really hope that this helps you achieve what you're looking for. In any case, that's it for this problem. We'll be continuing the playlist with the perfect squares problem. Thank you very much for watching.